Welcome to The Explainer. So today we're looking at something just truly mind-bending. When you look up at the night sky, you probably just see stars. But hiding up there in that endless black are honestly some of the most sophisticated, totally self-reliant machines humanity has ever built. I really want you to stop thinking of a spacecraft as just a vehicle and start thinking of it as an autonomous survival machine, one that's operating in literally the most unforgiving, deadly environment imaginable. So today, we're going to break down the anatomy of exactly how these incredible feats of engineering actually managed to stay alive out there. Here's our flight plan for today's explainer. We'll be hitting up number 1, survival machines. 2, extreme threats. 3, spacecraft anatomy. 4, systems engineering. And wrapping up with number 5, why they matter. All right, Section 1, survival machines, the ultimate vehicle. Let's go ahead and establish the incredibly high stakes of space travel. Okay, let's dive into this because contrasting airplanes with space vehicles completely reframes the whole engineering challenge. Think about an airplane, right? It flies in our atmosphere, it uses that air for aerodynamic lift, its engines literally breathe that air, and most importantly, when it lands, engineers can fix it. But space vehicles, they operate in a near-perfect vacuum. There's zero air for lift. Rockets actually have to carry both their fuel and their oxidizer just to fire their engines. They have to be entirely, completely self-sufficient in power, thermal control, propulsion, the whole shebang. And here's the real kicker. You can't just pull a satellite over for a quick chat with a mechanic. Once it leaves the launch pad, it's completely unrepairable. It just has to be perfect. Moving right along, Section 2, extreme threats. Surviving space. Let's look at the specific deadly environment these machines face the very moment that countdown hits 0. Well, the fight for survival starts violently. The spacecraft hasn't even reached space yet, but it's already undergoing immense physical punishment. Just during launch, the vehicle is subjected to severe vibrations, incredible acoustic loading just from the sheer roar of the rockets, violent shocks, and extreme acceleration. The structural design absolutely must withstand all of these launch loads flawlessly. Because think about it, if the structure is compromised here, the mission is literally over before it even begins. No way around it. Then, once it's actually up in space, the spacecraft faces extreme thermal whiplash. Because it's operating in a vacuum, there's no air to transfer heat via convection. So thermal control relies strictly on radiation. And when a spacecraft is out there exposed to direct sunlight, the surface temperatures can skyrocket to a blistering 120 degrees Celsius. That is seriously hot. But then, the very moment that spacecraft passes into the Earth's shadow, the temperature plummets instantly. We're talking dropping below negative 150 degrees Celsius. The vehicle must autonomously manage these drastic temperature swings, actively pumping and radiating heat to keep its delicate internal computers and instruments from, either melting or freezing completely solid. It's an incredible balancing act. And then, there are the invisible threats. The radiation environment in space is just relentless. Spacecraft are continuously bombarded by solar radiation, cosmic rays, and trapped charged particles swirling inside Earth's radiation belts. Over time, this radiation actively degrades electronic components and solar panels, so the machine is essentially decaying from the very moment it arrives up there. Engineers actually have to design it to survive its entire mission lifespan despite this constant invisible attack. So, how do we actually build a machine capable of surviving all of this? Well, that brings us to Section 3, Spacecraft Anatomy, Vital Subsystems. You see, a spacecraft isn't just a single machine. It's actually a complex collection of interconnected subsystems all working together. It's a lot like the organs in a human body, really. You have the structure, which acts as the skeleton. You've got propulsion, providing the muscle for thrust and orbital maneuvers, and the thermal system, acting as the temperature regulation. A failure in any one of these critical subsystems can completely jeopardize the entire mission. They all deeply depend on each other. Let's highlight a couple of these vital organs. First up is the Guidance, Navigation, and Control System, or GNC for short. Because communication delays from Earth can range anywhere from a few milliseconds to several hours for deep space missions, a spacecraft often literally has to think for itself. The GNC system allows the vehicle to autonomously determine its exact position and orientation out in the vastness of space, and it controls its motion to stay perfectly on target. Next is the Electrical Power System, or EPS. The absolutely crucial point here is that this is essentially the nervous system of the spacecraft. Without power, the machine is dead.
The EPS generates, stores, and distributes electrical energy to all the other subsystems. It provides the essential energy the spacecraft needs to feed and survive while in total isolation.
Now, with all these complex subsystems, piecing them together is a monumental task. This takes us to Section 4, Systems Engineering, the master puzzle. Space systems engineering is really the multidisciplinary brain behind the entire design. The hardest part of building a spacecraft actually isn't designing one single perfect part. It's making sure all the parts work together within incredibly strict constraints of mass, volume, power, and cost. As the source material highlights, a change in one subsystem affects several others, illustrating the importance of integrated design. It's like a giant high-stakes puzzle.
Let's move to the next concept and see how this builds. Imagine a client wants to add a slightly heavier camera to a satellite, just a small increase in payload mass. Well, that's step one. But step two, that extra weight means you now need stronger internal structures to survive launch, and possibly even a larger, way more expensive launch vehicle. Then step three, a heavier spacecraft means you need more propulsion to maneuver it, right? Which requires more fuel, which adds even more mass, which requires larger solar panels to power the extra weight. You see where this is going? It's a massive, cascading ripple effect, where just one small change alters the entire vehicle.
Because of these deeply intertwined systems and the fact that the spacecraft operates in a totally unrepairable environment, absolute reliability is required. Space systems engineers incorporate massive redundancy, meaning they literally have backup systems for their backup systems. They use fault-tolerant electronics and put the entire vehicle through extensive, rigorous testing before it ever even sees a launch pad. It just has to work perfectly the first time. All right, let's bring this massive billion-dollar engineering effort back down to Earth. Section 5, Why They Matter, Real-World Impact. And this brilliantly illustrates how all that extreme engineering directly powers our modern life. Communication satellites give us global internet and television. Navigation satellites, they power the GPS right in your phone. Earth observation satellites monitor our agriculture and water resources. Meteorological satellites give us our daily weather forecasts. And honestly, that's not even mentioning the scientific exploration of the distant universe or the critical national security infrastructure providing missile warnings and secure communications. We literally rely on them for everything. Which really leaves us with this final thought. These autonomous, incredibly self-sufficient survival machines are floating right now in a freezing, boiling, radioactive vacuum, just constantly fighting to stay alive. They can never be repaired, yet they dictate the everyday rhythm of modern human life. So, what would your day look like if this invisible, unrepairable web of autonomous spacecraft suddenly stopped surviving? It's a pretty fascinating reality to ponder, isn't it? Thanks for joining me on this explainer, and remember, keep looking up.